Hi, we are now going to take a look at a concept that was developed by Lodin Brendel back in 1904. And this is the concept of the boundary layer. What Brendel was able to do is he was able to unite the two fairly groups that exist in the fluid mechanics prior to 1904, and basically what exists was a split between the theoretician and experimental fluids mechanics. So, so the theoreticals sometimes were referred to as being a people who were involved in theoretical hydrodynamics. So the people that are involved in theoretical hydrodynamics look at the things such as potential invasive flow, flow equations, and velocity potential functions, and very mathematical. And now they acknowledge that the fact that the fluid were viscous, but their study was restricted to the fluids were, were restricted to the fluids where the viscous was assumed to be a small, and consequently that why they were looking at the thin inviscid flow related and just simplified the maths makes easier for them to study. And the other side were the experimentalists. So the experimentalists were fully aware of the fact that the flow was viscous. However, uh, they did is they conduct the experiment in order to understand what is happening within the fluids. So, so the people who are studying the hydraulics were typically experimentalists. Quite often are engineers in just coming up with empirical facts that they would fit their experimental data, or they curve to do the data, and then they could be used in it in designs and for things like that. These two different groups were really quite separate from one another, were not combined until the Lodin Prandtl came along with the boundary layer concept. So that was unable to the coupling between the when the Prandtl came did is that was enabled a coupling between the potential flow or the mathematical treatment with the viscous flow. Then the experimentalists had been doing, and it kind of unite these the two flows, the two fields. What we are going to do, we are going to take a brief look at what the boundary layer concept is, and then we'll spend a little bit more time to study the boundary layer equation. Okay, so let's we look at this. So what with this, what the boundary layer theory enabled was the knowledge of the fact that viscous was really once important in were very close to the wall. In this layer, we look into these simplest boundary layers. Look at this. Right, we have a uniform flow, and then with what Prandtl said viscosity is important, but is mainly confined a layer right near to the wall. Uh, so when we look into these boundary layers here, so here we have a boundary layer. So con- the simplest boundary layer that we can imagine was be like this. So that is mean there is a zero pressure gradient outside the flow. So at these areas, the P equal to P ATM. Alright. And then from this sketch, we can look like so that we have a schematic, a typical boundary layers, and we begin with a leading edge here. So this is a flat plate. So we begin with this, and then this is the beginning of the boundary layer. Typically, at this position, we say that the x equal to 0. So x is 0 at this area, at this position. So we have zero slit condition as well in the boundary layer. So this is a zero slit conditions along the wall, and so there is no velocity along the wall, but the effect of the wall filled by the fluids, and you go further downstream from the leading edge, and then the plate viscous diffusion is take the place so that the viscous diffuse up and away from the wall. So the region of the velocity deficit is lower than free stream velocity growth. So that that's why we say that boundary layer is flows. The boundary layer is growing on the flat plate. So the is a grow here. If you can see here, it's grow, and then the grow and the object as a flow goes over. So let's mean that for example you have any object, and then the boundary layer start to develop, and then you have another object, and then it must grow further, and so on. Okay, you could tip so okay, sorry, but the boundary layer usually begin with as a lamina. So at this point, actually this is a lamina unless you treat it as for example, you put the sandpaper here, so a little wire, for example, then you can create the turbulent boundary layer at the immediate position. So let's look at this. So this is a boundary layer, and then as they go along through this, and then they reach the position where we call it a transition. Okay, where at this transition, actually the lamina boundary layer has changed the profile. And then when it go further, it go to the what we call it the turbulent boundary layer, which is this is a infinite position. So it goes through, and then it always create the turbulent boundary layer. So this is a green line here we known as the boundary layer. Right, and then this is a non-slip condition as I mentioned early, and then this is a lamina. So what make we can determine or we can characterize type the flow whether it is a lamina, transitions or turbulence. So this how we do that is by looking at the Reynolds number. So normally we put the Reynolds number RE. As we know, the Reynolds number is as given in the flow in pipe. So we have the Reynolds number is like R U X over mu. So in this case, we use the X, and then normally we use a D in the pipe. So now we use the X. So that's why if you use the X, normally we return the Reynolds number like this, REX. If you see this. So when we go further, and then we meet the another transition. So then this is we call it the Reynolds number. So what we put this RE at critical. Okay, normally people know that the critical Reynolds number RE critical normally is about greater than in between, sorry, not greater, but this is in between 2100 and 2400. But this is Reynolds critical is for the only for the pipe, or we call it the internal flow. So, what is a RE critical for the external flow? This is given by 5 multiplied by 10 power of 5. This is for critical flow for the flat plate. This is for the, you must remember this. This is for the, for everybody must remember this number for the critical. So means that after Reynolds number, if the Reynolds number greater than this value, so means that the flow start to be a turbulent boundary layer. So the boundary layer unites. We know that the boundary layers normally depends on the Reynolds number, and then so that in the next segment we are going to look into the boundary layers in the detail of the boundary layer. But our focus in the next part is more sophisticated analysis, which is using the Navier-Stokes equations. All those we won't really to use to do that in this course, but we apply the previous course that we have studied in the chapter 1, and then we use a part of it, and then we simplified approach was developed by the von Karman, so that we can apply this in the boundary layer. So in the next segment, we will move into the von Karman momentum integral method. So hope that you can understand the fundamental of the boundary layer, where it's developed and then how it's developed. Okay, in this boundary layer, if you I will discuss further detail in this about this boundary layer in the next lecture.